One of the most fundamental questions we can ask about our universe itself is what makes it up. For a long time, the answer seemed obvious: matter and radiation. We observe them in great abundances, everywhere and at all times throughout our cosmic history. For some 100 years, we've recognized that, consistent with general relativity, our universe is expanding, and the way that the universe expands is determined by all the forms of matter and radiation within it. Ever since we realized this, we've strived to measure how fast the universe is expanding and how that expansion has changed over our cosmic history, as knowing both would determine the contents of our universe. In the 1990s, observations finally became good enough to reveal the answer: yes, the universe contains matter and radiation, as about 30% of the universe is made of matter, normal and dark combined, and about 0.01% is radiation today. But surprisingly, about 70% of the universe is neither of these, but rather a form of energy that behaves as though it's inherent to space: dark energy. The way this dark energy behaves is identical to how we'd expect either a cosmological constant in general relativity or the zero-point energy of space in quantum field theory to behave. But theoretically, this is an absolute nightmare. Here's what everyone should know. From a quantum point of view, the way we picture our universe is that real particles, quanta, exist atop the fabric of spacetime, and that they interact with one another through the exchange of virtual particles. We draw out diagrams that represent all the possible interactions that can occur between particles, Feynman diagrams, and then calculate how each such diagram contributes to the overall interaction between the multiple quanta in question. When we sum up the diagrams in increasing order of complexity, tree diagrams, one-loop diagrams, two-loop diagrams, etc., we arrive at closer and closer approximations to our actual physical reality. But there are other diagrams as well that we can draw out. Diagrams that don't correspond to incoming and outgoing particles, but diagrams that represent the field fluctuations that occur in empty space itself. Just like in the case of real particles, we can write down and calculate diagrams of ever-increasing complexity, and then sum up what we get to approximate the real value of the zero-point energy, or the energy inherent to empty space itself. Of course, there are a truly infinite number of terms, but whether we calculate the first one, the first few, or the first several terms, we find that they all give extremely large contributions. Contributions that are too large to be consistent with the observed universe by over 120 orders of magnitude. That is, a factor of over 10 power 120. In general, whenever you have two large numbers and you take the difference of them, you're going to get another large number as well. For example, imagine the net worths of two random people on one of the world's billionaires lists, person A and person B. Maybe person A is worth $3. 8 billion, and maybe person B is worth $1.6 billion, and therefore the difference between them would be $2.2 billion, a large number indeed. You can imagine a scenario where the two people you randomly picked are worth almost exactly the same amount, but these instances usually only occur when there's some relationship between the two, like they co-founded the same company or happen to be identical twins with one another. In general, if you have two numbers that are both large, A and B, then the difference between those numbers is also going to be large. Only if there's some sort of reason, an underlying symmetry, for example, or an underlying relationship between them, or some mechanism that's responsible for those two numbers to nearly perfectly match, will the difference between those numbers turn out to be very small compared to A and B themselves. The alternative explanation is that these two numbers really are very close together, but entirely coincidentally, something that's more and more unlikely the closer these two values are to each other. When we attempt to calculate, using quantum field theory, the expected value of the zero-point energy of empty space, the individual terms that contribute do so with values that are proportional to a combination of fundamental constants. For many decades, people have noted this property of the universe, that our predicted value of the zero-point energy of space is nonsensical. If it were correct, The expanding universe would have either recollapsed or expanded into empty nothingness extremely early on, before the electroweak symmetry broke and particles even received a non-zero rest mass, much less before atoms, nuclei, or even protons and neutrons could form. We knew that prediction must be wrong, but which of the following reasons explained why? The sum of all of these terms, even though they're individually large, will somehow exactly cancel. And so the real value of the zero-point energy of space is truly zero. The actual value of the zero-point energy of space takes on all possible values, randomly. And then only in locations where its value admits our existence can we arise to observe it. Or this is a calculable entity, and if we could calculate it properly, we'd discover an almost exact but only approximate cancellation, and hence the real value of the zero-point energy is small but non-zero. Of these options, the first is just a hunch that can't explain the actual dark energy in the universe, while the second basically gives up on a scientific approach to the question. Regardless of the answer, we still need to rise to the challenge of figuring out how to calculate the actual zero-point energy of empty space itself. If you're a physicist, you might imagine that there's some sort of miraculous cancellation of most of the possible contributions to the zero-point energy, but that a few contributions remained and do not have an equal and opposite contribution to cancel them out. Perhaps the contributions of all the quarks and antiquarks cancel. Perhaps the contributions of all the charged leptons, electron, muon, and tau, cancel with their antiparticle partners, and perhaps only the remaining uncancelled contributions actually account for the dark energy that exists in the universe. If we imagine that there's some sort of partial cancellation that occurs, what would we need to remain left over in order to explain the relatively tiny amount of dark energy that's present in the universe? The answer is surprising, something that corresponds to an energy scale of only a fraction of an electron volt. What sort of particles have a rest mass that's the equivalent of that particular energy value? Believe it or not, we have some right here in the Standard Model, neutrinos. As originally formulated, the Standard Model would have all of the quarks be massive, along with the charged leptons, the W and Z bosons, and the Higgs boson. The other particles, neutrinos and antineutrinos, the photon, and the gluons, would all be massless. In the aftermath of the hot Big Bang, in addition to the normal matter particles, protons, neutrons, and electrons that are produced, enormous numbers of neutrinos, antineutrinos, and photons are produced. About 1 billion of them, each, for each and every proton that survives. As it actually turns out, as we first suspected in the 1960 and then puzzled out in the 1990 and early 2000, neutrinos aren't massless at all. Rather, the species of neutrino or antineutrino, electron, muon, or tau, that's produced initially, isn't always the species of neutrino you observe later on. Whether passing through the vacuum of space or whether passing through matter, neutrinos have a non-zero probability of changing their flavor, which can only occur if they have mass. Otherwise, as massless particles, they wouldn't experience time, and so would have no period of oscillation. The fact that neutrinos have mass means necessarily that there's some property about them that the original formulation of the Standard Model doesn't account for. Since we don't know what exactly gives neutrinos these non-zero rest masses, we have to be very careful that we don't prematurely rule out a scenario that connects their mass scales to the energy scale of the observed dark energy that appears in the universe. Many have suggested plausible mechanisms for such a coupling, but no one has yet solved the hard problem of how do we calculate the zero-point energy of space using quantum field theory and the quantum fields that we know exist within our universe? We can measure the actual value of dark energy, but as far as understanding the theoretical side of the equation, we can only state, we do not. Another aspect of the story that needs to be included is the fact that, prior to the start of the hot Big Bang, our universe underwent a separate, earlier period where the universe was expanding as though we had a positive, finite value to the zero-point energy of space, cosmological inflation. During inflation, however, the energy was much larger than the value it has today, but still not as large as the expected Planck energy range values. Additionally, because there must be some sort of dark matter in the universe, some particle that isn't a part of the Standard Model, many have wondered if there couldn't be some connection between whatever particle is responsible for dark matter with whatever energy scale is responsible for dark energy. One particle that's a candidate for dark matter, the axion, typically comes in with very low masses that are below 1, but that must be greater than about a microelectron volt, which places it right in the range where it would be very interestingly suggestive for a connection to dark energy. But the hard problem still remains and remains unsolved. How do we know or calculate what the zero-point energy of empty space actually is, according to our field theories? That's something we absolutely must learn how to do. We have to learn how to do this calculation, otherwise we don't have a good theoretical understanding behind what is or isn't causing dark energy. And the fact is, we don't know how to do it. We can only assume it's all zero, except for some non-zero part. Even when we do that, we have yet to discover why the mass energy scale of dark energy takes on only this low but non-zero value. Any value seems possible. It must make us wonder, are we even looking at the problem correctly? But there is a great set of reasons to be hopeful. Observationally, we're making tremendous progress. 20 years ago, we thought that dark energy behaves as the zero-point energy of empty space, but our uncertainties on it were something like 50%. By 15 years ago, the uncertainties were down to about 25%. Now, they're down at around 7%. And with upcoming missions such as ESA's Euclid, the NSF's ground-based Vera Rubin Observatory, and NASA's upcoming Nancy Grace Roman Telescope scheduled to be our next flagship mission now that JWST has launched, we're poised to constrain the equation of state of dark energy to within 1%. In addition, we'll be able to measure whether the dark energy density has changed over cosmic time or whether it's been a constant over the past 8 billion years. Based on the data we have today, it's looking like dark energy is very much behaving as a constant at all times and locations, and that it's consistent with being the zero-point energy of empty space itself. However, if dark energy behaves differently from this in any way, the next generation of observatories should reveal that as well, with consequences for how we perceive of the fate of our universe. Even when theory doesn't pave the way to the next great breakthrough, improved experiments and observations always offer an opportunity to show us the universe as we've never seen it before, and show us what secrets we might be missing. Thank you so much for coming this far with us. Remember to join us in the next video. Until then, good night and remember to dream big.